Right now, scattered across the darkness of space, vast clouds of gas and dust are quietly giving birth to new stars. These cosmic nurseries, called nebulae, stretch across light years of silence, glowing in colors no earthly sunset could ever rival. Tonight, as your breathing slows and your body finds its rest, we will drift together through these immense, luminous cradles, where matter becomes starlight, and where the very atoms that compose your body were once forged. Let the darkness behind your eyes become the darkness between the stars, and let us begin. Welcome to Let's Learn While You Sleep. Tonight, we turn our gaze upward, far beyond the roof above your head, far beyond the thin blue envelope of our atmosphere, into the deep reaches of interstellar space, where some of the most beautiful and consequential structures in the universe reside. Nebulae, from the Latin word for mist or cloud, are enormous regions of gas and dust that can span dozens or even hundreds of light years across. Some are the birthplaces of stars, great stellar nurseries where gravity slowly gathers hydrogen and helium into dense cores that will one day ignite with nuclear fire. Others are the remnants of stars that have already lived and died, their outer layers cast into space in a final, radiant farewell. And still others are sculpted by the fierce radiation and stellar winds of the hottest, most massive stars in the galaxy. Together, they form a cycle of creation and destruction so vast and so patient that a single human lifetime is barely a heartbeat within it. So settle into your pillow, let your muscles release their hold on the day, and allow your mind to float outward into the quiet grandeur of the cosmos. To understand what a nebula truly is, we must first consider the nature of the space between the stars. It is tempting to think of interstellar space as a perfect vacuum, an absolute emptiness stretching from one star system to the next. And yet that is not quite the case. The space between the stars is filled with an exceedingly thin medium of gas and microscopic dust grains, a substance that astronomers call the interstellar medium. On average, in the general regions of our Milky Way galaxy, the interstellar medium contains roughly 1 atom per cubic centimeter, which is a density trillions of times lower than the air you are breathing right now. And yet, it is not nothing. Across the vast distances of interstellar space, even these vanishingly sparse particles add up to an enormous reservoir of matter. Scientists estimate that the interstellar medium accounts for roughly 10 to 15% of the total visible mass of our galaxy. Now, within this thin cosmic sea, there are regions where the gas and dust are considerably denser than average, sometimes hundreds or thousands of times denser. These denser regions are what we call nebulae. They are concentrations of hydrogen, helium, and trace amounts of heavier elements, laced with tiny grains of silicate and carbon dust, each grain often no larger than a fraction of a micrometer. What makes nebulae visible, what transforms them from invisible clouds into the breathtaking structures we see through telescopes, is light. Some nebulae glow because the gas within them has been energized by the ultraviolet radiation of nearby hot stars, causing the atoms to emit their own light. Others shine because they reflect the light of neighboring stars, much as fog reflects the glow of a street lamp. And still others reveal themselves not by glowing at all, but by blocking the light of more distant stars, appearing as dark silhouettes against the brighter background of the galaxy. Each type tells us something different about the conditions within these clouds and about the story of the matter that fills them. Consider for a moment how remarkable it is that something so thin, so diffuse, so seemingly insubstantial, can be the foundation upon which entire star systems, entire worlds are built. Among the most celebrated nebulae in all of astronomy are the Emission Nebulae, those great luminous clouds that glow with their own light in vivid shades of red, pink, and sometimes green or blue. The mechanism behind their radiance is elegant in its simplicity. Within or near these clouds, there exist extremely hot, massive stars, often young stars of spectral types O and B, whose surface temperatures can exceed 30,000 degrees Kelvin. These stars pour out torrents of ultraviolet radiation, photons with energies high enough to strip electrons from the hydrogen atoms in the surrounding gas, a process called photoionization. When those freed electrons eventually recombine with hydrogen nuclei, they release energy in the form of visible light. In the case of hydrogen, the most common transition produces a distinctive red glow at a wavelength of approximately 656 nanometers, a color known to astronomers as hydrogen alpha emission. This is why so many emission nebulae appear in deep, rose-like shades of red and pink. But hydrogen is not the only element at work. Doubly ionized oxygen, for instance, produces a striking teal-green emission, while ionized nitrogen contributes hues of crimson and violet. The interplay of these emissions, layered across varying densities and temperatures of gas, creates the spectacular palette that has made nebulae some of the most photographed objects in the cosmos. Perhaps the most famous example is the Orion Nebula, also known by its catalogue designation Messier 42, which lies approximately 1,344 light-years from Earth in the constellation Orion. Visible to the unaided eye as a faint, fuzzy patch in Orion's sword, it spans roughly 24 light-years across and contains enough mass to form thousands of stars. Deep within its glowing heart lies the trapezium cluster, a tight grouping of hot young stars whose ultraviolet radiation illuminates the surrounding gas with that unmistakable rosy glow. When you gaze at the Orion Nebula, you are witnessing star formation in progress, a process that has been unfolding there for roughly 2 million years. And that will continue long after all memory of our civilization has faded into silence. Not all nebulae generate their own light. Some shine only because they borrow it. Reflection nebulae are clouds of interstellar dust and gas that are not hot enough, nor sufficiently energized by nearby radiation to emit their own photons. Instead, they scatter the light of neighboring stars, reflecting it toward us across the light years in much the same way that a bank of fog scatters the beam of a headlight. And here is a beautiful detail, one that connects these distant clouds to something as familiar as the sky above your head. The dust grains within reflection nebulae tend to scatter shorter wavelengths of light more efficiently than longer ones, a process known as Rayleigh scattering, the same phenomenon that makes Earth's daytime sky appear blue. As a result, reflection nebulae often appear in soft, ghostly shades of blue, even when the star illuminating them is white or slightly yellow. One of the loveliest examples is the nebulosity surrounding the Pleiades star cluster, also known as the Seven Sisters, located roughly 440 light-years from Earth in the constellation Taurus. The Pleiades themselves are a group of hot blue-white stars, and the faint wisps of blue nebulosity draped around them are reflection nebulae, dust that the cluster happens to be passing through, illuminated by the star's light. For centuries, cultures around the world have told stories about the Pleiades. The ancient Greeks saw them as seven sisters pursued across the sky. The Maori of New Zealand call them Matariki and celebrate their rising as the beginning of a new year. The Lakota people of North America saw in them a story of children carried to the heavens. And yet, the delicate blue veils of reflected starlight surrounding them were not confirmed until the age of astrophotography in the late 19th century. There is something quietly moving about this, that a phenomenon so ethereal, so faint, waited so patiently for our technology to catch up with its beauty. And then there are the dark nebulae, clouds so dense with dust that they block virtually all visible light from objects behind them. They appear as inky silhouettes against the glowing backdrop of the Milky Way. The most famous is the Horsehead Nebula in Orion, a pillar of cold, dense dust sculpted into a shape reminiscent of a horse's head, backlit by the Emission Nebula IC 434. Deep within the coldest and densest regions of certain nebulae, something extraordinary and patient is taking place. Something that unfolds across hundreds of thousands of years and yet determines the fate of entire solar systems. Star formation. It begins in what astronomers call molecular clouds, vast, frigid nebulae, where temperatures can drop to just 10 or 20 degrees above absolute zero, around minus 250 degrees Celsius. At these extreme temperatures, hydrogen atoms pair together to form molecular hydrogen, and the cloud becomes opaque to visible light, hiding its interior from our view. Within these dark, quiet clouds, small regions of slightly higher density begin to exert a gravitational pull on the surrounding gas. Perhaps a shockwave from a nearby supernova compresses one part of the cloud. Perhaps the passage of a spiral arm in the galaxy creates a ripple of pressure. Whatever the trigger, once a region becomes dense enough, its own gravity begins to draw in more material, and a slow, inexorable process of collapse begins. This collapsing region is called a protostellar core. As it contracts, it heats up. Conservation of angular momentum causes it to spin faster and flatten into a disk. At the center, temperatures and pressures climb steadily. Over tens of thousands of years, the core temperature reaches millions of degrees Kelvin, and at that point, hydrogen nuclei begin to fuse into helium, releasing enormous amounts of energy. A star is born. The remaining disk of gas and dust around the young star becomes a protoplanetary disk, the raw material from which planets, moons, asteroids, and comets will eventually form. Our own solar system arose from just such a disk approximately 4.6 billion years ago. Every grain of iron in your blood, every atom of calcium in your bones, was once part of a nebular cloud, not unlike the ones we are contemplating tonight. The pillars of creation, those iconic columns of gas and dust in the Eagle Nebula, photographed by the Hubble Space Telescope in 1995, are perhaps the most vivid illustration of this process that humanity has ever captured. Those towering pillars, each several light-years tall, are regions of dense gas being sculpted and slowly eroded by the ultraviolet radiation of nearby hot stars, even as new stars continue to form within their shadowed interiors. Stars do not live forever, and when certain types of stars reach the end of their lives, they return much of their material to the interstellar medium in the form of planetary nebulae and supernova remnants, two of the most visually stunning phenomena in the cosmos. Let us consider planetary nebulae first, and let us set aside a common misconception. Despite their name, planetary nebulae have nothing to do with planets. The term dates back to the 18th century, when the astronomer William Herschel observed these objects through his telescope and noted that their round greenish disks resembled the planet Uranus. The name stuck, even though we now understand their true nature. A planetary nebula forms when a star of low to intermediate mass, roughly between 1 and 8 times the mass of our Sun, exhausts the hydrogen fuel in its core. Over millions of years, the star swells into a red giant, its outer layers expanding far beyond their original boundaries. Eventually, these outer layers are gently expelled into space, forming an expanding shell of ionized gas around the remnant core, which is now a small, extraordinarily hot object called a white dwarf. The ultraviolet radiation from the white dwarf illuminates the expanding shell, causing it to glow in spectacular colors. The Ring Nebula in the constellation Lyra, catalogue designation Messier 57, is one of the best-known examples. Located roughly 2,300 light-years from Earth, it appears as a glowing elliptical ring of green and red gas surrounding a tiny central star. The green hue comes from doubly ionized oxygen, while the red at the outer edges is produced by hydrogen and nitrogen emission. Another breathtaking example is the Cat's Eye Nebula, designated NGC 6543, which displays an astonishingly complex series of concentric shells and jets that scientists believe were produced by episodic mass ejections from the dying star over thousands of years. Planetary nebulae are transient by cosmic standards. They typically persist for only 10 to 20,000 years before dispersing into the surrounding interstellar medium. And yet, in that brief window, they achieve a beauty that seems almost deliberate, as if the dying star wished to leave behind something luminous, something that might be seen and wondered at from across the galaxy. When a star far more massive than our Sun reaches the end of its life, it does not depart quietly, it detonates. A supernova is one of the most violent events in the known universe, an explosion so powerful that for a brief period the dying star can outshine an entire galaxy of hundreds of billions of stars. And what it leaves behind, the expanding cloud of debris, is called a supernova remnant. Consider the Crab Nebula, located approximately 6,500 light-years from Earth in the constellation Taurus. On July 4th, 1054, Chinese astronomers recorded the sudden appearance of a brilliant guest star in the sky, so bright it was visible during the daytime for roughly 23 days. What they witnessed was a supernova, and the Crab Nebula is the remnant of that explosion, still expanding outward at approximately 1,500 kilometers per second, nearly 1,000 years later. At its center lies a pulsar, a rapidly rotating neutron star, barely 20 kilometers across, spinning roughly 30 times per second and emitting beams of radiation like a cosmic lighthouse. The Crab Nebula glows with a tangled web of filaments in red, blue, and white, each color representing different physical processes, from synchrotron radiation produced by electrons spiraling in magnetic fields to the familiar emission of ionized hydrogen and oxygen. Another spectacular supernova remnant is the Veil Nebula in the constellation Cygnus, the remains of a star that exploded roughly 8,000 years ago, now forming a delicate lacework of glowing filaments spanning roughly 110 light-years across. Supernova remnants are far more than beautiful wreckage. They are among the most important structures in the galaxy for the evolution of matter. The extreme temperatures and pressures generated in a supernova are responsible for forging elements heavier than iron, elements like gold, platinum, and uranium, which cannot be produced by the normal fusion processes inside stars. When a supernova remnant disperses into the interstellar medium, it enriches the surrounding gas with these heavy elements, seeding future generations of stars and planets with the raw materials for complexity, for chemistry, and ultimately for life itself. Somewhere in that vast procession of nebulae, between the stellar nurseries and the remnants of stellar death, there exists a profound and beautiful cycle, a cosmic recycling that has been turning for billions of years and that connects every generation of stars to every other. Astronomers sometimes call this the galactic matter cycle, and understanding it transforms the way we see the night sky. Here is how it unfolds. A molecular cloud, cold and dense, collapses under gravity to form a new generation of stars. Those stars burn through their nuclear fuel over millions or billions of years, fusing hydrogen into helium, helium into carbon, carbon into oxygen, and in the most massive stars, continuing up the periodic table to iron. When those stars die, whether gently as planetary nebulae or violently as supernovae, they return their enriched material to the interstellar medium. This material mixes with the existing gas and dust, and over millions of years, new molecular clouds form, denser now, richer in heavy elements than the clouds that preceded them. And from these new clouds, a new generation of stars is born, stars whose planets can now incorporate heavier elements into their composition, elements like silicon and iron that form rocky worlds, elements like carbon and oxygen that form the basis of organic chemistry. Our Sun is believed to be a third-generation star, sometimes described as a population 1 star in astronomical terminology, meaning it formed from material that had already been processed through at least 2 previous generations of stellar birth and death. The nebula from which our solar system collapsed was already rich in the heavy elements that would become the earth beneath your feet, the water in your glass, the calcium in your bones. Every atom of carbon in your body was fused in the core of a star that lived and died before our Sun was born. Every atom of iron in your blood was forged either in the final moments of a massive star's life or in the cataclysm of its supernova explosion. You are, in the most literal and scientifically precise sense, made of stardust, of material that was once part of a nebula, that was once part of a star, that was once part of the primordial hydrogen formed in the first few minutes after the Big Bang. Let us rest now with one of the most magnificent nebulae ever observed, the Carina Nebula, a sprawling complex of gas and dust located approximately 7,600 light-years from Earth in the southern constellation of Carina. Spanning more than 300 light-years across, it is one of the largest and brightest nebulae in our sky, though it is best seen from the southern hemisphere. The Carina Nebula is a showcase of nearly every nebula process we have discussed tonight. Within its boundaries, you will find emission regions glowing in vivid hydrogen alpha red, reflection regions shining in scattered blue, dark dust pillars silhouetted against the brighter gas behind them, an active star formation occurring within dense molecular cores. One of its most remarkable inhabitants is Eta Carinae, a massive, unstable binary star system that contains at least one star, estimated to be roughly 100 times the mass of our Sun and approximately 5 million times as luminous. In 1843, Eta Carinae underwent what astronomers call the Great Eruption, a colossal outburst that briefly made it the second brightest star in the night sky, despite its enormous distance. The eruption expelled roughly 10 to 40 solar masses of material into space, forming the Homunculus Nebula, a small bipolar nebula shaped like two expanding lobes centered on the star. Astronomers believe that Eta Carinae is nearing the end of its life and may explode as a supernova at some point in the coming hundreds of thousands of years, though predicting exactly when is beyond current capabilities. When it does, it will likely be visible from Earth in daylight. The Carina Nebula was among the first targets observed by the James Webb Space Telescope, which released its initial images in July of 2022. Those images revealed previously unseen details in the nebula's structure, including hundreds of previously hidden young stars and jets of material being ejected from newborn stellar systems. The infrared eyes of the Webb telescope can peer through the dust that obscures visible light, revealing the hidden machinery of star birth in breathtaking clarity. As you lie here tonight, consider that this immense cloud, this cathedral of gas and light, is simultaneously creating and destroying, building new stars, even as it is shaped and eroded by the stars already blazing within it. There is another class of nebulae that often escapes the attention of casual stargazers, but captivates those who study the deep structure of galaxies. These are the superbubbles and supershells, enormous cavities blown into the interstellar medium by the combined stellar winds and supernova explosions of entire clusters of massive stars. Imagine not a single star exploding, but dozens or hundreds of massive stars, born together in a great cluster, living out their brief, brilliant lives, and then detonating one after another over the course of a few million years. The cumulative effect of their winds and explosions can carve out a cavity in the surrounding gas hundreds of light years across, sweeping the material outward into a dense, expanding shell. These structures are immense. The Orion Eridanus superbubble, for instance, is a cavity roughly 1,200 light-years across that extends from the Orion star-forming region downward through the constellation Eridanus. It was carved by the winds and supernovae of the massive stars in the Orion OB1 association over the past 10 to 12 million years. We are, in fact, living within a similar structure. Our solar system currently resides within what astronomers call the local bubble, a region of unusually hot, low-density gas roughly 1,000 light-years across. Current evidence suggests that the local bubble was created by a series of supernova explosions that occurred approximately 14 million years ago, and research published in 2022 by Catherine Zucker and colleagues demonstrated that virtually all nearby young star-forming regions sit on the surface of the local bubble, suggesting that the expanding shell of the bubble compressed surrounding gas and triggered new episodes of star formation. In a sense, the very existence of the star-forming clouds we see in our neighborhood of the galaxy, the clouds from which new solar systems are being born today, may owe their origins to the deaths of stars that exploded millions of years before our sun was born. Here is the cycle once more, writ large across the sky: death feeding birth, destruction sculpting creation, the galaxy endlessly remaking itself out of its own ashes. As our journey deepens, let us turn our attention to the tools and techniques that have allowed humanity to study nebulae in such exquisite detail. For the story of nebulae is also the story of how our eyes have grown sharper across the centuries. To the ancient observers, the few nebulae visible to the unaided eye were simply fuzzy patches of uncertain nature. The Persian astronomer Abd al-Rahman al-Sufi, in his book of fixed stars, written around the year 964, recorded the Andromeda galaxy as a small cloud, though he could not have known its true nature. The French astronomer Charles Messier, in the 18th century, compiled his famous catalogue of nebulous objects largely as a convenience for comet hunters, identifying over 100 objects that might be mistaken for comets. His catalogue includes many of the nebulae we have discussed tonight, including Messier 42, the Orion Nebula, and Messier 57, the Ring Nebula. The invention of spectroscopy in the 19th century revolutionized our understanding. When William Huggins turned a spectroscope toward the Cat's Eye Nebula in 1864, he discovered that its light consisted of a few discrete emission lines rather than a continuous spectrum, proving that it was a cloud of glowing gas rather than a collection of unresolved stars. This was a turning point, the moment when nebulae became understood as physical environments rather than mere smudges of light. In the 20th and 21st centuries, telescopes operating across the electromagnetic spectrum, from radio waves to X-rays, have revealed nebulae in entirely new dimensions. Radio telescopes can detect the cold molecular hydrogen, invisible at optical wavelengths. Infrared telescopes, like the Spitzer Space Telescope and now the James Webb Space Telescope, can peer through dust to reveal hidden star formation. X-ray observatories like the Chandra Telescope reveal the superheated gas within supernova remnants, glowing at temperatures of millions of degrees. Each wavelength tells a different part of the story, and together, they compose a portrait of nebulae richer and more complete than any single instrument could achieve alone. And still, there is more to learn, more hidden detail waiting for the next generation of telescopes, the next advancement in sensitivity, the next quiet night of patient observation. Yet, for all the precision of modern instruments, some of the most enchanting qualities of nebulae remain matters of perspective and patience. Take, for instance, the concept of a nebula's color as we perceive it. Many of the spectacular nebula images you may have seen, those vivid tapestries of crimson, teal, and gold, are not exactly what your eyes would see if you could somehow float beside them in a spacecraft. The human eye, adapted for the savannas and forests of Earth, is not well suited to the faint, diffuse light of a nebula. Most nebulae, even the bright ones, would appear as pale, ghostly grey-green wisps to the unaided human eye, because at such low light levels, our retinas rely primarily on rod cells, which do not perceive colour as richly as cone cells do. The vibrant colours in nebula photographs are real, in the sense that the light at those wavelengths is genuinely being emitted by the gas, but they are often captured through long exposures and narrowband filters that isolate specific emission lines, rendering visible the otherwise invisible richness of the spectrum. Some images use a technique called the Hubble palette, in which the light from ionized sulfur, hydrogen alpha, and doubly ionized oxygen are mapped to red, green, and blue channels respectively, even though the actual wavelengths of sulfur and hydrogen alpha emission are both in the red portion of the spectrum. This creates images that are scientifically informative and visually stunning, but they are translations, beautiful and faithful translations, of a reality our unassisted eyes cannot fully grasp. There is a gentle lesson in this. The universe is far richer than our senses can apprehend. Much of its beauty lies in wavelengths we cannot see, in timescales we cannot experience, in scales we cannot directly comprehend. And yet, through ingenuity and patience, we have built instruments that extend our senses into these hidden realms, revealing wonders that no eye in the history of life on Earth had ever witnessed before the modern era. Every nebula image is an act of translation, a bridge between the cosmos and the human mind, rendered in the language of light and color that our visual cortex can understand. Our nebulae so immense, so all-encompassing, that we do not merely observe them from the outside. We live within one. Our solar system is embedded within a structure called the local interstellar cloud, a warm, tenuous nebula roughly 30 light-years across, with a temperature of approximately 6,000 to 7,000 degrees Kelvin, and a density still far less than any vacuum achievable in a laboratory on Earth. The local interstellar cloud is itself situated within the larger local bubble we discussed earlier, drifting through the hot, low-density interior of that ancient cavity. The boundary of the local interstellar cloud meets the solar wind, the stream of charged particles flowing outward from our Sun, at a region called the heliopause, which lies roughly 120 astronomical units from the Sun. Beyond the heliopause, the interstellar medium begins. The Voyager 1 spacecraft crossed this boundary in August of 2012, becoming the first human-made object to enter interstellar space. Voyager 2 followed in November of 2018. Both spacecraft are now drifting through the outermost fringes of this nebula, sending back data about the conditions of the interstellar gas that surrounds our entire solar system. There is something quietly astonishing about this. When we look at photographs of distant nebulae, we tend to think of them as remote, separate places, vast and unreachable. And yet, we are inside a nebula right now. The atoms of interstellar gas that surround our solar system are the outermost tendrils of the same type of material that forms the great clouds we have been contemplating tonight. The boundary between our home and the wider galaxy is not a wall, but a gradient, a gentle transition from the sun's influence to the interstellar wind. And somewhere out there, the Voyager spacecraft continue their silent journey through that wind, carrying with them a golden record of sounds and images from Earth, a message in a bottle drifting through the cosmic fog. It will be 40,000 years before Voyager 1 passes within roughly 1.6 light-years of the star Gliese 445 in the constellation Camelopardalis. By then, whatever remains of the spacecraft will be a silent relic, but the nebula through which it travels will still be there, patient and unchanged. As we approach the quieter reaches of our journey tonight, let us consider one more type of nebula, one that stretches our understanding of scale to its very limits. These are the intergalactic nebulae, filaments and clouds of gas that exist not within galaxies, but between them, in the vast cosmic web that connects the large-scale structure of the universe. For decades, astronomers theorized that much of the normal or baryonic matter in the universe was unaccounted for. We could see stars and gas within galaxies, but the total mass of visible matter fell short of what cosmological models predicted should exist. Current evidence strongly suggests that this missing matter resides in a warm, hot, intergalactic medium. Filaments of diffuse gas heated to temperatures between 100,000 and 10 million degrees Kelvin, stretching between galaxy clusters along the filaments of the cosmic web. These structures are incredibly faint and difficult to detect, but observations in the X-ray and ultraviolet portions of the spectrum, combined with sophisticated simulations, have begun to reveal them. In 2020, a team of researchers using data from the European Space Agency's XMM Newton X-ray telescope reported the detection of a warm, hot gas filament connecting two galaxy clusters, providing some of the most direct evidence yet for this intergalactic medium. The filaments of the cosmic web are the largest known structures in the universe, stretching across hundreds of millions of light-years. If individual nebulae are the cradles of stars, then these intergalactic filaments are the scaffolding upon which the entire architecture of the cosmos is built. Galaxies form at the intersections of these filaments, like dewdrops collecting at the junctions of a spider's web. And the gas within these filaments, though unimaginably diffuse, represents a reservoir of matter that may one day fall into galaxies and participate in future generations of star formation. The story of nebulae, it turns out, does not end at the borders of our galaxy. It extends outward, connecting the smallest molecular cloud to the largest structures in the observable universe, a continuous web of gas and light and gravity that spans the entire cosmos. And so we arrive at the gentlest part of our journey, the place where knowledge softens into wonder, and wonder softens into rest. Tonight, we have traveled through the interstellar medium, that faint ocean of atoms between the stars, and we have watched it gather into the great clouds we call nebulae. We have seen Emission nebulae glowing with the borrowed energy of hot young stars, their hydrogen singing in shades of red. We have drifted past reflection nebulae, those quiet mirrors of scattered blue light, and through dark nebulae, those patient silhouettes that hide the machinery of creation within their dusty depths. We have followed the journey of a collapsing molecular cloud as it gave birth to a new star. And we have watched dying stars return their substance to the cosmos, enriching the interstellar medium with the heavy elements that make planets and life possible. We have peered into the hearts of supernova remnants, those luminous monuments to stellar death. And we have traced the great cycle of galactic recycling that connects every generation of stars to every other. We have learned that we ourselves live within a nebula, that the boundary between our solar system and the wider galaxy is not a wall, but a whisper, and that the Voyager spacecraft are even now drifting through the tenuous interstellar gas that connects us to the rest of the Milky Way. And we have stretched our vision outward to the cosmic web itself, those vast intergalactic filaments along which the entire architecture of the universe is strung. All of this, every cloud, every star, every shining remnant, is part of a single, continuous process that has been unfolding for nearly 14 billion years and that shows no sign of ending. The nebulae are not just objects to be studied. They are chapters in a story that includes us, a story written in hydrogen and starlight, in gravity and time. As your thoughts begin to soften now, as the edges of consciousness grow quiet and warm, carry with you the knowledge that you are part of this story. The atoms in your body remember the nebulae from which they came, and one day, in the very distant future, they will return to the interstellar medium to drift and gather once more, perhaps to become part of a new cloud, a new star, a new world. Rest now, knowing that you belong to the cosmos, and the cosmos belongs to you. Let us linger for a moment longer in the deeper quiet of this cosmic nursery, and consider the way nebulae speak to us across the void. They do not speak in words, of course, nor in any vibration our ears could detect, and yet they communicate with extraordinary eloquence through the language of light itself. Every photon that reaches our telescopes from a distant nebula carries within it a kind of signature, a fingerprint of the atom that released it. When astronomers spread that light into a spectrum, they see bright lines and dark lines at very specific wavelengths, each one corresponding to a particular chemical element. This technique, known as spectroscopy, was developed in the 19th century by scientists including Gustav Kirchhoff and Robert Bunsen, who demonstrated that each element absorbs and emits light at characteristic frequencies. It was through this elegant method that we first learned what nebulae are made of without ever traveling to them, without ever touching their substance. The bright emission lines of hydrogen glow at a wavelength of approximately 656 nanometers, a deep and tender red that gives so many nebulae their rosy hue. Oxygen, doubly ionized by the fierce radiation of nearby stars, contributes a haunting teal-green glow, particularly prominent in planetary nebulae, where the exposed core of a dying star bathes its shed layers in ultraviolet fire. Nitrogen adds its own subtle warmth, and sulfur contributes deeper reds that blend with hydrogen into tapestries of color that no painter could quite replicate. And so, without setting foot beyond this small blue world, we have read the chemical poetry of clouds that drift tens of thousands of light years away. Consider how remarkable that is. The same hydrogen that fills your body, that courses through every cell in quiet molecular partnership with oxygen, is the same hydrogen whose spectral signature blazes across the Orion Nebula. The iron in your blood was forged in the heart of a massive star and scattered by a supernova whose remnant may now be a nebula glowing faintly in some distant arm of the galaxy. You are not merely observing these structures from afar. You are, in the deepest and most literal sense, made of the same substance, reading a message written in your own elemental alphabet, a letter from the family of matter to which you have always belonged. There is a particular kind of nebula that deserves a gentle visit before we drift further into rest, one that carries within it a quiet sorrow and a profound beauty. These are planetary nebula, and despite their name, they have nothing at all to do with planets. The term was coined by the astronomer William Herschel in the late 18th century, because through the small telescopes of his era, these objects appeared as round, softly glowing disks that resembled the faint greenish circles of distant planets like Uranus, which Herschel himself had discovered in 1781. In truth, a planetary nebula is the final exhalation of a sun-like star, the last breath of a life that may have burned steadily for 10 billion years. When a star of roughly our sun's mass exhausts the hydrogen fuel in its core, it begins to burn helium and swells into a red giant, expanding to perhaps 100 times its former diameter. Eventually, the outer layers of this bloated star grow so loosely bound that they drift away into space, pushed by gentle stellar winds and pulses of radiation from the increasingly exposed core. What remains at the center is a white dwarf, an object roughly the size of Earth, yet containing nearly the mass of the entire original star, so dense that a single teaspoon of its material would weigh several tons. This tiny, intensely hot remnant, with surface temperatures that can exceed 100,000 degrees Kelvin, floods its shed envelope with ultraviolet radiation, causing the expanding gas to fluoresce in breathtaking patterns. The Ring Nebula in the constellation Lyra, catalogued as Messier 57, is one of the most beloved examples. A delicate hoop of glowing gas roughly 1 light-year across, approximately 2,300 light-years from Earth. The Helix Nebula, sometimes called the Eye of God, stretches nearly 6 light-years in diameter and is one of the closest planetary nebulae to our solar system, lying roughly 650 light-years away. Each of these objects is a memorial, a luminous farewell that will itself fade over tens of thousands of years as the gas disperses and the white dwarf slowly cools toward darkness and silence. Yet, even as planetary nebulae speak of endings, there are nebulae that speak of something far more violent, far more dramatic, and strangely, far more generous. These are supernova remnants, the shattered remains of stars that did not fade gently, but instead detonated with a brilliance that, for a few weeks, can outshine an entire galaxy of hundreds of billions of stars. A supernova occurs when a massive star, one perhaps 8 or more times the mass of our Sun, exhausts all possible nuclear fuel and can no longer support itself against the relentless inward pull of its own gravity. The core collapses in a fraction of a second, and the resulting shockwave tears the star apart, flinging its enriched outer layers into the surrounding space at velocities that can reach tens of thousands of kilometers per second. The most famous supernova remnant in our sky is the Crab Nebula, located in the constellation Taurus, roughly 6,500 light-years from Earth. It is the remnant of a supernova that was observed and recorded by Chinese astronomers in the year 1054. A guest star so bright it was visible in daylight for nearly 3 weeks. At the heart of the Crab Nebula spins a pulsar, a neutron star barely 20 kilometers across, yet spinning approximately 30 times every second, sending beams of radiation sweeping through the cosmos like the beam of a lighthouse. The material flung outward by that ancient explosion is still expanding, still cooling, still weaving itself into the interstellar medium, where it will one day contribute its heavy elements to new clouds, new collapses, new stars. This is the profound generosity of supernovae. The carbon in your muscles, the calcium in your bones, the phosphorus in your DNA, nearly every element, heavier than hydrogen and helium, was forged either in the cores of massive stars or in the catastrophic seconds of their explosive deaths. You carry within you the legacy of supernovae that blazed and faded long before our own sun began to form, roughly 4.5 billion years ago, from a cloud already salted with these ancient gifts. As your breathing slows and the weight of the day dissolves a little further, let us visit one last kind of nebula, perhaps the most mysterious and the most quietly beautiful of all. These are dark nebulae, clouds so dense with dust that they block the light of everything behind them, appearing as silhouettes against the brighter backdrop of the Milky Way. They do not glow, they do not shimmer, they simply absorb, and in their absorbing, they create some of the most striking and haunting shapes in the night sky. The most famous is the Horsehead Nebula in the constellation Orion, a pillar of cold, dense dust that rises against the faint red glow of the Emission Nebula, IC 434 behind it. Its shape, which resembles the head and mane of a horse in profile, is roughly 3.5 light-years from base to tip, and it lies approximately 1,500 light-years from Earth. Within these dark clouds, temperatures can drop to as low as 10 degrees above absolute zero, roughly 10 Kelvin, cold enough for molecules to form that would be torn apart in warmer, more exposed regions of space. It is here that complex molecules begin to assemble, including water, ammonia, methanol, and even simple organic compounds that scientists believe may be among the precursors to the chemistry of life. The Coalsack Nebula, visible from the southern hemisphere as a dark patch against the bright band of the Milky Way near the constellation Crux, was known to Aboriginal Australian cultures for thousands of years, often interpreted as the head of a great emu stretching across the sky. What appears to be emptiness is, in truth, fullness, a reservoir of raw material waiting for the slow hand of gravity to begin its patient work. Dark nebulae are the quiet rooms of the galaxy, the places where creation gathers itself in silence before announcing its presence in light. And there is something deeply comforting in that thought as you rest here now, in your own quiet darkness, gathering your own energy for whatever dawn may bring, knowing that stillness is not absence but preparation, that the dark is not empty but full of patient becoming. Let's turn now to something truly extraordinary, a phenomenon so vast that it stretches across light years of space, yet so delicate in its structure that it seems almost painted by an unseen hand. These are the dark nebulae, the silhouettes of the cosmos, and they are among the most hauntingly beautiful features in the entire night sky. Unlike the Emission nebulae that glow with their own radiance, or the reflection nebulae that shimmer with borrowed starlight, dark nebulae are known to us precisely because they block the light of everything behind them. They are clouds of molecular hydrogen and interstellar dust, so thick, so profoundly dense, that not even the brilliance of a million background stars can pierce their depths. When astronomers first observed these regions, some believed they were simply empty patches of sky, voids where no stars existed. It was the American astronomer Edward Emerson Barnard who, in the early 20th century, began to catalogue these dark markings systematically, recognizing them not as absences, but as presences, as real structures of matter drifting through the galaxy. His catalogue, published in 1927, listed hundreds of these objects, and many still bear his name today. The Barnard 68 cloud, for instance, is a nearly perfect dark globule located roughly 410 light-years from Earth, a small, cold pocket of gas and dust that appears as an inky void against the rich star fields of the Milky Way. It is only about half a light-year across, modest by cosmic standards, and yet within that modest volume, temperatures hover near just 16 kelvins, barely above absolute zero. And here is where the story grows tender, because these dark nebulae, these seemingly lifeless shadows, are in truth among the most fertile places in the universe. Deep within their cold interiors, far from the disruptive heat and radiation of nearby stars, molecules of hydrogen drift close together, drawn by gravity's patient hand. Over hundreds of thousands of years, these molecules accumulate, and the core of the dark nebula grows ever denser, ever colder, until at last, the conditions become just right for something remarkable to begin. That remarkable beginning is the birth of a protostar, the earliest stirring of what may one day become a sun. And it happens in silence and darkness, hidden entirely from view. Within the densest cores of dark nebulae, gravity finally overwhelms the gentle outward pressure of the gas, and the cloud begins to collapse inward upon itself. This process, known as gravitational collapse, unfolds over tens of thousands of years, a timescale that is both staggeringly long by human measure and breathtakingly brief by cosmic ones. As the core contracts, it heats up, and deep within that cocoon of dust and cold hydrogen, temperatures begin to climb from mere tens of kelvins toward hundreds, then thousands. The object that forms at the center is not yet a star, not in the way we would recognize one, but rather a warm, glowing knot of compressed gas, still gathering material from the surrounding envelope, like a seed drawing water from dark soil. Astronomers call this a protostar, and it radiates most of its energy not as visible light, but as infrared radiation, the kind of gentle warmth that our eyes cannot see, but that specialized telescopes, like the Spitzer Space Telescope, and more recently, the James Webb Space Telescope, can detect with remarkable clarity. And so it was that when astronomers pointed these infrared instruments at the seemingly barren patches catalogued by Barnard and others, they discovered that the darkness was teeming with activity. Hundreds of protostars, some still deeply embedded in their natal clouds, were found glowing softly at wavelengths invisible to the human eye. Consider how beautiful that notion is, that the emptiest-looking regions of the sky are in truth nurseries of extraordinary energy and potential. The darkness is not absence. It is incubation. It is the universe taking its time, gathering its strength, preparing something luminous within a place where no light yet escapes. And in this way, the dark nebulae remind us that stillness and silence are not the opposites of creation, but rather its most essential companions. For every star that has ever shone began its life wrapped in a blanket of perfect, patient night. Now let us drift a little further and visit one of the most celebrated nebulae in all of modern astronomy, a structure so visually arresting that its image has become synonymous with the wonder of deep space itself. This is the Pillars of Creation, a formation within the Eagle Nebula, also catalogued as Messier 16, located roughly 6,500 light-years from Earth in the constellation Serpens. The pillars were made famous by an image captured by the Hubble Space Telescope in 1995. And that photograph changed the way many people thought about the universe, revealing towering columns of gas and dust that rose like ancient monuments from the floor of a vast cosmic cathedral. The tallest of the three main pillars stretches approximately 4 light-years from base to tip, a distance so immense that light itself, traveling at roughly 300,000 kilometers per second, would need 4 full years to traverse its length. And yet, despite their grandeur, the pillars are fragile things, sculpted by the intense ultraviolet radiation streaming from a cluster of young hot stars nearby, stars that were themselves born from the very same nebula only a few million years ago. This radiation is slowly eroding the pillars, boiling away their outer layers of gas in a process astronomers call photoevaporation. At the tips of the pillars, small, dense knots of gas resist this erosion a little longer than their surroundings, and within some of these knots, new stars are forming even now, sheltered briefly from the destructive light that surrounds them. These tiny cocoons of potential are called evaporating gaseous globules, and they represent one of the most poignant scenes in all of astrophysics. Stars being born inside structures that are themselves being destroyed. When the James Webb Space Telescope captured the pillars again in 2022, its infrared vision peered through the dust and revealed dozens of newly forming stars that Hubble could never have seen. The pillars glowed with an ethereal translucence, and what had once appeared opaque and solid was shown to be gossamer and luminous, like curtains of dust drawn across a nursery of newborn light. So we begin to see a pattern, a rhythm, woven into the very fabric of the cosmos, one that echoes softly through every nebula we have visited tonight. It is the rhythm of creation and dissolution, of matter gathering and dispersing, of light emerging from darkness and eventually returning to it. The hydrogen atoms drifting through a nebula tonight may once have been part of a star that burned for billions of years and then scattered itself across space in a supernova explosion. Those same atoms may now be settling into the core of a new dark cloud, beginning the long, quiet journey toward becoming part of another star, another world, perhaps another sky, under which some other form of awareness might one day look upward and wonder. This is what astronomers sometimes call the galactic ecosystem, the continuous recycling of matter and energy through the interstellar medium. And it is one of the most profound discoveries of modern astrophysics. Roughly 90% of the visible matter in our galaxy exists in the form of stars, but the remaining fraction, the gas and dust spread between them, is not inert or purposeless. It is the reservoir from which all future stars will be drawn, and the repository into which all dying stars will eventually pour their enriched material. Each generation of stars forges heavier elements in its core, elements like carbon, oxygen, nitrogen, and iron. And when those stars die, they seed the surrounding nebulae with these elements, making the next generation of stars and planets chemically richer than the last. Our own solar system, born approximately 4.6 billion years ago from a cloud of gas and dust in some long-vanished nebula, carries within it the accumulated legacy of countless stellar generations that came before. The calcium in your bones, the iron in your blood, the oxygen you breathe as you listen to these words, all of it was forged inside stars and distributed through nebulae long before the Earth existed. You are not merely looking at the cosmos from a distance. You are part of its ongoing story, a quiet chapter written in stardust, resting now beneath a sky that remembers everything. Let us now turn our attention to a different kind of nebula, one that speaks not of birth, but of endings, and of the quiet grace with which a star can leave the universe more beautiful than it found it. These are planetary nebulae, and despite their name, they have nothing at all to do with planets. The term was coined in the 18th century by the astronomer William Herschel, who noticed that some of these objects resembled the pale, round disks of distant planets when viewed through the telescopes of his era. The name remained a gentle artifact of early misunderstanding, even as our knowledge deepened. A planetary nebula forms when a star of low to intermediate mass, perhaps 1 to 8 times the mass of our Sun, reaches the final chapter of its existence. Over billions of years, such a star steadily fuses hydrogen into helium in its core, and when the hydrogen begins to run low, the core contracts and heats, igniting helium fusion and causing the outer layers to swell enormously. The star becomes a red giant, its atmosphere expanding to hundreds of times its original radius, sometimes engulfing inner planets entirely. And then, across tens of thousands of years, those swollen outer layers are gently expelled into space, pushed outward by stellar winds and radiation pressure, unfurling like a slow exhalation into the surrounding void. What remains at the center is a white dwarf, the exposed core of the former star, incredibly dense and blazing hot, sometimes reaching surface temperatures of over 100,000 degrees Kelvin. This tiny remnant, often no larger than the Earth, yet containing a mass comparable to the Sun, floods its shed envelope with intense ultraviolet radiation. That radiation excites the atoms in the expanding shell of gas, causing them to glow in breathtaking colors. Oxygen radiates in soft teals and greens, nitrogen in delicate reds, and hydrogen in the warm pinks that photographers and astronomers have admired for centuries. The result is a luminous, sculpted structure, sometimes spherical, sometimes butterfly-shaped, sometimes ringed like a cosmic eye, each one a portrait of the star that made it. Perhaps the most beloved example of a planetary nebula is the Ring Nebula, catalogued as Messier 57, resting quietly in the constellation Lyra, roughly 2,300 light-years from Earth. When Charles Messier first recorded it in 1779, it appeared as little more than a faint, hazy oval, a smudge of light barely distinguishable from surrounding stars. Today, with the instruments available to modern astronomy, and especially with observations from the James Webb Space Telescope released in 2023, we can see its structure in extraordinary detail, a barrel-shaped shell of gas viewed nearly along its axis, giving us the illusion of a perfect ring. At its heart lies the remnant white dwarf, a stellar ember with a surface temperature estimated at roughly 120,000 degrees Kelvin, flooding the surrounding gas with energy. The inner region glows in shades of blue and violet, where highly ionized helium emits its characteristic light. Further out, the cooler regions radiate in green from doubly ionized oxygen, and the outermost edges blush with the deep reds of hydrogen and nitrogen. These colors are not painted on, they are the authentic signatures of atoms responding to energy, each element glowing at wavelengths determined by the architecture of its electron shells. And surrounding the visible ring, astronomers have discovered faint halos and tendrils of gas extending far beyond the bright core, evidence of earlier episodes of mass loss, gentle exhalations, the star released thousands of years before the final expulsion. Consider for a moment the timescale of what you are seeing. The central star may have begun shedding its outer layers roughly 4,000 years ago, and the nebula will continue to expand and fade over the next 10,000 years or so, growing ever dimmer until it dissolves entirely into the interstellar medium. It is, in cosmic terms, a fleeting monument, a brief and luminous memorial to a star that burned for billions of years. And yet, in that brevity, there is something profoundly moving. The knowledge that even endings can be radiant, that the matter cast off by this dying star will drift among the clouds of the galaxy, enriching them, seeding them with the elements from which future stars and worlds may one day form. Let the nebulae dissolve now into the warm darkness behind your eyes. Let the light of distant stars become soft and indistinct, like candles seen through a gentle fog. There is nothing more you need to hold on to tonight, no fact to remember, no image to preserve. Everything we explored is already part of you, woven into the atoms of your body, written into the history of the matter from which you are made. Your breath moves in and out like the slow expansion of a planetary nebula, gentle and unhurried. Your heartbeat is steady, a quiet rhythm in the vast silence. The universe continues its patient work around you, stars forming and dying, nebulae glowing and fading, the great cycle turning. And you are here, safe and warm, a small and precious part of it all. Let sleep come now, easily and naturally, the way starlight travels through space, without effort, without resistance, simply flowing toward wherever it is meant to go. Good night. If this journey through the nebulae brought you a sense of peace tonight, consider leaving a gentle note in the comments about which nebula captured your imagination. And if you would like to drift through more of the cosmos with us, the subscribe button is just a quiet touch away. Thank you for spending your night with Let's Learn While You Sleep. Subscribe and come back tomorrow night. We'll be here. Sleep well.